In question number 9, a particle is projected from point A. It collides with a vertical smooth wall 1 at point B. It then collides horizontally with a vertical smooth wall 2 at point C, parallel to wall 1, and finally lands at point D. If coefficient of restitution is E for each collision and T is the total time of flight, then we have to find out the value of E and T. So let's analyze the situation. Whenever a collision occurs, then it will change the component of velocity in horizontal direction. The vertical component of velocity will remain same. So we can say that the time of ascent is equal to the time of descent. So in that situation, if Vx is the horizontal component of velocity of the ball, of the particle, then we can write d divided by Vx, this is the time from A to B, plus d divided by Evx, that is the time from B to C, and that must be equal to d divided by E square Vx, that is the time from C to D. So on solving this, the value of E comes out to be root 5 minus 1 divided by 2. So option A is correct and B is wrong. Now we have to find the value of capital T. So if I see the motion of this ball, so at the instant when it's rebound from C, it have a horizontal velocity E square Vx and its vertical velocity is 0. Now it has to travel a distance of 5 meter to cover the vertical height. So we can say that 5 is equal to half into g into t square. So the time taken from C to D comes out to be 1 second. So the total time of flight is 2 seconds. So option C is also correct. So the correct answer for question number 9 are option A and C. Let's move to question number 10. In question number 10, two bodies of masses m and 2m are connected by a massless spring of spring constant 3k, and arrangement is placed over smooth horizontal surface. When spring was in its natural length L0, masses m and 2m are given velocities 4 meter per second and 1 meter per second at t equal to 0 as shown. If t1, t2 are the time instants when mass m and 2m have minimum speed vm and v2m respectively, then we have to find out the validity of given options. So if I solve this problem in the frame of center of mass, then if I calculate the velocity of center of mass, it comes out to be 4 into m plus 2m into 1 divided by 3m. So it comes out to be 2 meter per second. So in the frame of center of mass, the velocity of this m is 2 meter per second in this direction at t equal to 0, and the velocity of 2m mass is 1 meter per second in this direction at t equal to 0. So at t equal to 0, now we have to find out what is the minimum speed of mass m, that is Vm. So the minimum speed of mass m occurs when the mass m is moving in this direction with a velocity of 2 meter per second with respect to center of mass. So with respect to ground, its velocity then becomes 0. So Vm at that instant is equal to 0. So option A is correct. Let's check the validity of option B. V2m is equal to 1 meter per second. That is the minimum speed of 2m mass. So the minimum speed of 2m mass occurs at this moment at t equal to 0. So the velocity of 2m at this instant is velocity of 2m with respect to center of mass, that is minus 1, plus velocity of center of mass is 2. So it comes out to be 1 meter per second. So option B is also correct. Now V2m equal to 1 meter per second occurs at t equal to 0. So the value of T2 must be equal to 0. So option D is wrong. And in order to find out the value of T1, the value of T1 is equal to capital T by 2, because this motion takes a time interval of t by 2. So we have to find out what is the value of t for this given system. So the value of time period for this system can be written as capital T is equal to 2 pi under root m, where m is the reduced mass of system, so that is 2m by 3 divided by k, that is 3k. So it comes out to be 2 pi under root of 2m by 9k. So option C is also correct. So the correct answer for question number 10 are option A, B and C. Let's move to question number 11. In question number 11, four traveling waves having equation y1, y2, y3 and y4 are superimposed with each other. If y0 is the equation of motion of particle at x equal to 0 and ymax is the maximum displacement of any medium particle from its mean position, then we have to find out the value of y0 and ymax. So if I find out the resultant traveling wave, y resultant, so this is equal to y1 plus y2 plus y3 plus y4. So if I solve this mathematics, then this resultant comes out to be 10 sine kx plus 3 pi by 8 into cos of omega t plus 19 pi divided by 360. So this is the resultant traveling wave. Now we have to find out what is the ymax. So ymax is 10. So option B is correct. And in order to calculate the value of y0, we must substitute the value of x is equal to 0 in this equation. So we will find that option A is also correct. So the correct answer for question number 11 are option A and B. Let's move to question number 12. In question number 12, a charged particle whose q by m ratio is 1 is thrown with velocity 5 I cap meter per second from origin in a gravity-free space where a uniform magnetic field 4 I cap plus 3 j cap Tesla exists. If d is the maximum separation of charged particle from xy plane and v is the velocity of the charged particle at this time, then we have to find out d and v vector. So let's analyze the situation. If I take the component of velocity along the direction of magnetic field v parallel, so that is this angle is 37 degree because b is given 4 I cap plus 3 j cap. So if I take the component of velocity along the direction of magnetic field, so v parallel comes out to be 5 into cos 37 degree, that is 4 by 5. So it comes out to be 4 meter per second. Similarly, if I take the v perpendicular component which is in this direction at this moment, so that comes out to be 5 into 3 by 5, so 3 meter per second. Now we know that this is the case of helix. So the maximum separation of the charged particle from the xy plane can be written as d is equal to 2r. So that can be written as 2 into r. R can be written as m into v perpendicular divided by q into b. So if I substitute the data, 2 into m by q is 1, v perpendicular is 3 and the magnitude of magnetic field is 5. So this can be found out as 6 by 5 meter. So option A is correct. Now we have to find out what is the velocity of the charged particle at this instant when d is equal to 2r. So at this instant we can see that the perpendicular velocity is in this sense, and if I write the velocity, then it can be found out as v parallel component is 4 into 4 I cap plus 3 j cap by 5. So if I write the velocity this in x and y, then this can be written in this way. Similarly, if I write the perpendicular velocity in x and y, then it can be written as 3 times minus 3 I cap plus 4 j cap by 5. So if I solve this, then it comes out to be 1.4 I cap plus 4.8 j cap meter per second. So option B is also correct. So the correct answer for question number 12 are option A and B. Let's move to question number 13. In question number 13, a particle of mass m by 4 moving with velocity 4v0 collides with a rod of mass m and length 2l perpendicularly at end A and comes to rest after collision. Rod is placed over smooth horizontal xy plane and magnetic field B is directed perpendicular to the plane. If delta V is the magnitude of induced EMF between A and B and Vb is the speed of end B just after collision, then we have to find out the value of Vb and delta V. So let's analyze the situation. After collision, the velocity of mass m by 4 becomes 0. So if I write the angular momentum equation about point O, then we can write m by 4 into 4v0, that is mv0 into L is equal to I. So I for the rod can be written as m into L square, 2L square by 12 into omega. So if I solve this, the value of omega comes out to be 3V0 by L. So if I find out the velocity of point B, Vv, so that can be written as V0 minus omega into L. So that can be written as V0 minus 3V0. So it comes out to be minus 2V0. So option B is correct and D is wrong. Now we have to find out the magnitude of induced EMF between A and B. So I have to find out VB minus VA. So this can be further written as VO minus VA minus of VO minus VB. So if I take a small element at a distance x of length dx, which is moving in this direction with a velocity v plus omega x. So for this, if I write the induced EMF from O to A, then that can be written as VBL. So V plus omega x into B into L, that is dx, integration from 0 to L. Similarly, if I take a small element at a separation x in this direction of length dx, and its velocity in this direction is v0 and in this direction is omega into x. So I am writing in this way, minus of omega x minus v0. So this is v0 into b into dx, again from 0 to L. So if I solve this equation, it comes out to be 2b v0 into L. So integration is from 0 to capital L. So the answer would be 2b v0 L. So option C is also correct. So the correct answer for question number 13 are option B and C. Let's move to question number 14. In question number 14, consider a parallel AC circuit. I1, I2 and I are currents in respective branch as shown in figure. If P is the average power delivered by source, choose the correct options. So we have to find out the value of I, I2 and P. So in this question, so if I write the impedance of this LCR branch, then it comes out to be root 2 ohm. And if I write the impedance of this LCR branch, then its Z comes out to be 2 root 2 ohm. So the current I1 can be written as 100 root 2 divided by root 2. So 100 sine omega t, and the current is lagging by a phase of pi by 4. So minus pi by 4. Similarly, if I write for I2, then I2 can be written as V0 divided by Z. So 50 into sine omega t minus pi by 4. Again the current is lagging by a phase of pi by 4. So if I find the value of I2, so I2 value is correct. Now I have to find out what is the value of I. So the net value I is summation of I1 and I2. So if I do the summation of this I1 and I2, then I will get 150 sine omega t minus pi by 4. So option A is also correct. Now we have to find out what is the average power delivered by the source. So average power delivered by the source is IRMS. So the value of IRMS is 150 by root 2 VRMS. So VRMS is 100 into cosine of phase phi. So that is pi by 4. So the value of cos pi by 4 is 1 by root 2. So on solving, this comes out to be 7500 watt. So option C is also correct. So the correct answer for question number 14 are option A, B and C. Let's move to question number 15. In question number 15, a monochromatic point source of light S, wavelength lambda, is placed symmetrically at a normal distance d from two plane mirrors M1 and M2 as shown. Interference pattern is observed on the screen placed at a large distance capital D. Intensity of light on screen at point O due to source only is 2I0. It means the direct intensity at point O due to this source is 2I0. And after each reflection, intensity becomes half. If IR is the resultant intensity of light at O, then we have to find out the value of IR. So in the given question, the intensity of light due to source at point O is 2I0. So in that case, if I consider the amplitude of this source as A, then we can say that 2I0 is equal to K times A square. Since the intensity after reflection becomes half, so it means that the intensity of the source at this point is I0 and its amplitude can be taken as A by root 2. In the same way, intensity of this source is I0, so its amplitude can be taken as A by root 2. So due to symmetry, we can see that the resultant of this source and this source can be written as A by root 2 into 2. So their resultant can be written as root 2A. So now we have two sources, one is this and the other is this, whose amplitude is A. So in order to find out the resultant amplitude at this point due to these sources, so in order to calculate the phase difference between them, we have to find out what is the path difference. So the path difference delta x can be written as this separation is 2d, this separation is d, so this length can be written as under root of d square plus 2d whole square, and due to this is minus d, this is the path difference due to optical path difference, plus there is a path difference due to reflection of light from the plane mirror, so that is lambda by 2. So if I solve this, then it comes out to be 2d square by capital D plus lambda by 2, and it is given that the value of 2d square by capital D is 99 lambda. So this is 99 lambda plus lambda by 2. So if I write the resultant intensity at point O, then it can be written as root 2 minus 1 into A whole square into K times, that is resultant intensity. So we know that the value of K square is 2I0. So this can be written as 2I0 into root 2 minus 1 whole square. So on further solving, it comes out to be 2 times I0 into 3 minus 2 root 2. So if I check the options, then option B is correct, and in option D it is given that interference pattern on the screen above and below the point O is same. So this is correct due to the symmetry. So the correct answer for question number 15 are option B and D. Let's move to question number 16. In question number 16, let MP and Mn denote the mass of proton and neutron respectively, and M1 and M2 denote the mass of neon nucleus and calcium nucleus respectively. Then choose the correct statements. We know that the binding energy per nucleon increases up to iron, that is Fe56. So we can say that then the binding energy per nucleon of calcium is more than the binding energy per nucleon of neon. So if mass defect in calcium is more, then we can say that M2 must be less than 2 times M1. So option B is correct. Now we know that the experimental mass of the nucleus is always less than its theoretical mass. So 2 times M1 is less than 20 times mass of neutron plus mass of proton. So option C is also correct. So the correct answer for question number 16 are option B and C. Let's move to the first paragraph containing question number 17 and